These sets of notes are going to go over 5 types of chemical reactions. The first one I'm going to talk about is synthesis. Synthesis is what happens when you have 2 or more reactants and you make one product. So these are some generically written chemical equations. So just to give you sort of the format. So you could have A plus B, so 2 reactants in this case, producing one product. So basically they're coming together and forming one larger compound. Or you could have more than that. You could have 2 or more. So in this example over here, it's 3 reactants producing one product. But the idea is that you have a bunch of smaller compounds over here combining together and forming one larger compound. So here are some actual examples of synthesis. So I can see that I have multiple reactants here and I'm forming a single product. Again, I've got multiple reactants forming a single product, and in this case, I've got even more, again, forming a single product. And so that is what synthesis is. You've just got many reactants forming a single product. The next type of chemical reaction is decomposition, sometimes known as analysis. In this case, you'll have one single reactant, but it breaks down into multiple products. So again, here's sort of a generic formula for that. Here is our one reactant forming multiple products. And again, it doesn't have to be 2, it could be 3, it could be 4 or 5. Typically they don't get that big, but they could. Here are some actual examples of that. So here is a single product single reactant forming multiple products. A second example here, it's one large product, again, forming multiple products. Do I keep saying products all the time? One reactant forming multiple products. All right. The next one here we have is combustion. Now, synthesis and decomposition are pretty straightforward. Combustion requires a number of things to have to happen in order for it to be considered combustion. So in combustion, you have a hydrocarbon. So a hydrocarbon is a compound that is formed of carbons and hydrogen. So hydrogen, carbon, carbons. So there has to be carbons and hydrogens in order for it to be a hydrocarbon. A lot of our hydrocarbons will also have other elements. So if there's like an oxygen or nitrogen present, those will also be considered hydrocarbons. So a hydrocarbon by definition just has a lot of hydrogen and carbons in it. So in order for it to be combustion, it has to have 4 very specific things. There has to be a hydrocarbon of some sort. It has to react with oxygen gas. So it has to react with oxygen gas. And you have to produce carbon dioxide and water. So all 4 of those things need to happen in order for us to consider it combustion, just as our definition for class. And these reactions often release or produce heat. So there will be an explosion or fire or some sort of heat being released, and so that heat is a product of the reaction, so we would write it on the product side. So again, a hydrocarbon has to react with oxygen gas, it has to produce carbon dioxide and water. So here are a couple of examples. We've got CH4, which is a hydrocarbon reacting with oxygen gas. It's going to produce carbon dioxide and water. And again, this is going to be combustion, so it is going to produce energy at the end. Our second example is, this is basically respiration. It's the opposite of photosynthesis. It's what our cells do in order to utilize sugar as energy. So we've got sugar here, which is a hydrocarbon. It's going to react with oxygen gas. It's going to produce carbon dioxide and water. And then it's also going to make ATP, which is a energy molecule, so it's also going to produce energy. All right, so that is combustion for you. Let's see. We've got two more. Our next reaction is a single replacement reaction. In this case, we're looking at ionic compounds, or an acid, and we'll get into acid-base reactions later. So we're going to be looking at ionic compounds, and so ionic compounds are always made up of a cation and an anion. And remember, your cation is positively charged and your anion is negatively charged, and they attract each other and they form a neutral compound. And your cation is always written first and your anion is always written second. So in a single replacement reaction, we can have a cation bonded to an anion, and then you have a single metal over here that's not bonded to anything. And in some cases, that metal is super reactive, and that metal will swap and steal the other cation's partner. So remember, the cation always wants to be with an anion. And so when that happens, that cation is now bonded to the anion, leaving that original cation A all by itself. So the metal basically replaces another metal. So A was a metal, C is a metal, and then C steals A's partner. Or you could have it so your anions are actually the thing that is switching. So again, you have a cation, it's hanging out with its anion, and if you have a nonmetal sitting over here, what happens sometimes is if this nonmetal is really reactive, it's going to steal the other anion's partner. So it's going to try to pair up with that metal. We always write our cation first, so I write my X first. Z has stolen X as a partner, leaving Y all by itself. Okay, so that's how a single replacement reaction takes place. Here are some examples of that. So in this case, I have aluminum. Aluminum is a metal, so it forms a cation. I've got lead nitrate, so lead is a cation. Nitrate is a polyatomic ion. I think I gave you a list of them, and this has a negative charge. And then what's going to happen here is aluminum is going to want to steal a partner, and because aluminum is positively charged, it's going to want to pair up with nitrate. And that's going to leave lead all by itself. I do like writing the pluses and minuses. I do find it helpful when looking at my notes. In the reaction where there are nonmetals that are switching partners, again, here's sodium. Bromine is my nonmetal, so it's the anion. Chlorine is a nonmetal, so it will normally form an anion. And because chlorine is all by itself, it wants to steal itself a partner. So it's going to want to pair up with that sodium. So then I'm going to end up with sodium chloride, and then bromine will end up all by itself. Now, we don't have to worry about this because you guys won't be predicting products, but typically this only happens if the single element is more reactive than the one that's already in the bond. But we're not going to be predicting any reactions. You just have to be able to identify it when you see it. The last one is a double replacement reaction, and this is when two aqueous ionic compounds basically exchange partners. So they're going to exchange ions and form two new ionic compounds. I do like to think about this in terms of dancing. So it's like two dance couples just switching partners. So again, these are ionic compounds, and remember, ionic compounds are a cation bonded to an anion. So cation and an anion. We always write our cations first. And all that's happened here is my cations and my anions have switched partners. Right? So now instead of A being paired up with B, A is now paired up with D instead. Same thing with C. C is no longer paired with D. C is now paired with B. Now, again, we don't have to predict products, so you don't have to worry about this part. You just have to be able to identify a double replacement reaction when you see one. So here are some examples of double replacement reactions. So if I'm looking at this, I see zinc chloride and potassium hydroxide. Again, another polyatomic ion. I have a list of them for you that you can reference. And all that's happened here is now zinc, instead of being paired with chloride, is now paired with the hydroxide. And the potassium is no longer paired with the hydroxide. The potassium is now paired with the chloride. They have switched Dan's partners. Therefore, this is a double replacement reaction. All right, same thing down here. HNO3 and then NaOH. This is actually an acid-base neutralization, and we'll talk more about those later, but those are often also double replacement reactions. So hydrogen was paired with nitrate. Again, you can look at the polyatomic list. Sodium is paired with hydroxide. Again, another polyatomic. And all that has happened is our cations and anions have switched partners. So NaNO3, so Na is now paired with NO3, and our H and our OH are now together. And if you're looking at HOH, what's cool is it's 2 hydrogen and 1 oxygen, so it is actually H2O. And then we'll practice more of this in class.